The third skill in this unit addresses the tangent graphs, and then the fourth skill addresses the reciprocal graphs for each of these. So the last one we're going to look at this week is tangent. My advice would be to be really strong at sine, cosine, and tangent because we can quickly graph the reciprocals if we are good at the original graphs. So in the investigations, what we saw with tangent is that its period is actually pi. It actually can get through a cycle in half the measurements that it takes sine and cosine, and that the amplitude is none because of the shape of tangent graph. And here are the coordinates if you'd like to use those coordinates to graph. So since the period is pi, we're only trying to fill in those 5 points from 0 to pi. So if we make pi the fourth mark after 0, we want to count by these pi over 4s. At 0, the tangent is 0, and at pi over 4, it's 1. And then, oops, sorry about that. At pi over 2, it's undefined. And we're just going to write that in our chart, and we'll see how that interprets on the graph. At 3 pi over 4, it's -1, and at pi, it's back to 0. So what you're seeing here, I'll label by fourths, is you're seeing 0, 0, pi over 4, 1, and then because it's undefined at pi over 2, just like we did with our rational graphs, we mark this asymptote. So what's happening is there's a curve connecting these 2 points, and then as it approaches that asymptote, it goes up towards infinity. And then you have -1 and 0, so this curve is looking like this. So notice this is what it does every 5 points. It goes from 0 up to infinity, undefined, -1, back to 0. After 0, remember, it would go up to this other point we're plotting. Then there would be the other asymptote. So I'm extending this to give you guys a bigger picture so that you realize between the two asymptotes, that's a period of the tangent graph. But remember, a period should encompass 5x values total the way that we're splitting it up to graphs. So this would be my starting point, then 1, 2, 3 in between, and then the asymptote, and that would be the 5 values. I really don't want you guys to forget that there's these 3 points that you're plotting in between so that you don't accidentally do the wrong pattern when you're trying to extend the tangent graph. So we're going to go ahead and graph this the same as we did others. So we already did all of our sine and cosine graphs. So looking at our tangent graphs, so this tangent function doesn't really need to be rewritten. So it has an a value of 2, which means there's a vertical stretch. Everything's getting multiplied by 2. And there's a b value of 3, which means there's a horizontal, everything's going to get multiplied by 1/3, so we're going to call that a compression. So our period for tangent is normally pi, unless there's been a horizontal stretch or compression, and here there's been a horizontal compression. So the period's going to be pi over 3. And the amplitude remains none. Now we plot points that are usually 1 unit away, so we still can use that if you like to graph without the chart and use the patterns. So if you'd like to graph without the chart and use the patterns, remember that we normally see our starting point and then 4 more marks to finish our period, which is normally at pi. And we see it go up, usually by 1, and then this is our asymptote, and then the point below and back up. And these points are usually 1 unit apart. Even though we don't call that the amplitude here, it's still kind of the same type of measurement. So we did see a vertical stretch in this function. So I would expect in this graph, instead of being 1 apart, that those midline points and the upper ones or lower ones are 2 units apart. There was no shift up or down, so the midline of the function is still at 0. And then there's no reflection, so I do expect to start and still follow this same pattern of points. And then I'd want to know if there is a shift in the starting point and how to scale it. So as far as scaling goes, for the y values, the midline is still at 0, but the amplitude is 2, so we just want to be able to at least fit 2 units from 0 there. But we're going to go above and below that, so we're going to have to see a little more. And then normally we scale it so that fourth mark is our period of pi. In this case, our period is pi over 3. So we want that fourth mark to be pi over 3. And remember, if you're figuring out what that means for what you're actually counting by on your scale, you're going to split that up since it's the fourth mark. That means each individual mark is kind of counting by pi over 12s. So 1 pi over 12, 2 pi over 12 would be pi over 6. 3 pi over 12 would be pi over 4. 4 pi over 12 would be pi over 3. 5 pi over 12, 6 pi over 12, 7 pi over 12, 8 pi over 12, 9 pi over 12, and then it would continue, and then you would have the negative counterparts over on this other side. So I'm just going to fill some of those in at least. Etc. And then, like I said, the midline wasn't moved up and down, and there was no shift left or right. So I do expect my first point to start right at 0, 0, and then just go through that pattern. But that I expect a vertical stretch of 2. So this would be the first point. At the next mark, I would expect it to go up to 2 and then be undefined. And then from -2 back up to that mark. And I expect these curves here, but I'm also keeping in mind that I know to complete the period, there's another point within each branch of this graph before I plot the asymptote. I've set it up so that throughout each period, if I start with 0 and end with that period mark, I plot 5 points in total, and I want to make sure we see those, so I could extend it this way as well, and this would be my asymptote here. And then you could keep going with that pattern. If you do prefer the points to plot, you would start with that tangent parent function. So you're just copying this down from what we had before. 0 to 1, undefined, -1 back to 0. And you would just do the transformation. So we just had a horizontal compression of 1/3 and a vertical stretch of 2. And you would see the same points that we are getting on that graph. And you could plot those instead. The domain is a little bit tricky for the tangent function because you have those asymptotes. So just like our rational function, it's all real numbers, but with these exclusions, the range is a little bit simpler. So when we look at the domain, I'm going to let you guys assume that we mean all real numbers when we say x cannot equal. So I'm not going to make you say the all real numbers before it, but you may in your future math classes, so be prepared to do so. So I'm just going to let you tell me what x cannot equal. And to understand this, we're going to have to look at a pattern. And we've done this before with the range for the greatest integer function. So I see that x can't be -pi over 6, +pi over 6, +pi over 2. Those are the places where the asymptotes are occurring. So if you need to, you can make yourself a little list. We call this a sequence of numbers. And this has a pattern because remember, these asymptotes are occurring every period of the pi function. Okay, so they are separated by 1 period. So you either know that because you've already calculated the period. So we already calculated the period and it's pi over 3. Or you can literally subtract the different values. If I do pi over 6 minus -pi over 6, I get 2 pi over 6, which is pi over 3. And if I did it again for pi over 6 and pi over 2, if I do pi over 2 minus pi over 6, that's like 6 pi over, 3 pi over 6 minus pi over 6 is 2 pi over 6, which again reduces to pi over 3. I can see that the numbers in this list are separated by a distance of pi over 3, whether I see it this way or I see it this way. So what this means is the numbers that x cannot be are numbers that are pi over 3 apart. So if you remember how we say that, we say pi over 3 times k, because you could multiply that by any negative or any positive as long as k is an integer. But then we have to make sure we've actually started at an official point. So you need to pick one of these as your starting point. So let's say I pick pi over 6. I'm saying you can't be anything that is this far away from pi over 6 or any multiples of it. Okay, so again, how I got this is where one of the asymptotes occurs. This is how far apart the asymptotes are. And k is always an integer to account for using that pi over 3 one time or 2 times or 3 times in the negative or in the positive direction. And then our range here, because you see these branches goes towards infinity and negative infinity, is all real numbers, or if you like to use the interval notation, negative infinity to infinity. So we're going to try one more tangent example. And this one has the weird scaling, so if you didn't watch the extra example from the sine one from the skill 1 and 2 notes, you can go through this here. So this doesn't really need to be rewritten. Pi over 3 is the b value. It's literally the only transformation here. And that means there will be a horizontal, and so think what's going to happen. Things are going to get multiplied by 3 over pi. Pi is slightly bigger than 3. It's like 3.14. That means things are getting multiplied by something that's just a little bit smaller than 1. So this is technically a horizontal compression. Okay. How that affects my graph. My period is normally pi for a tangent function. However, horizontally, things are getting compressed by getting multiplied by this 3 over pi. And this is going to make our period 3. So it's actually going to make the numbers on our x-axis more familiar, but not what we're used to when we're graphing trig functions. The amplitude is none because it's a tangent function, but there's also no vertical stretch or compression, so I expect my parent function points to still be 1 unit apart. So again, when I'm graphing here, I'm used to seeing this branch where the next thing is undefined, and then below and back to the middle, like this. And I still am going to expect these to be 1 apart, even though there's not technically amplitude here. There is still that vertical measurement, and it hasn't been stretched or compressed. The midline would still be at 0. There's no shifting up or down here, so I still expect that to stay. And there's no horizontal shift and there's no reflection, so I don't expect a different starting point or a different sequence of points. I basically expect this exact same thing, except for instead of this being pi, I expect it to be 3 because the period's now 3. So I expect the fourth mark on that x-axis to be 3. Because there's no change in amplitude, I'm still going to expect those values about the same. To then understand what each mark on this graph means, since I know the fourth mark is labeled as 3, as we've been doing, I'm going to take a fourth of that, and that means each mark represents 3/4. So 3/4, 3/4 plus 3/4 would be 6/4, or 3 over 2. 6/4 plus another 3/4 would be 9/4. 9/4 plus another 3/4 would be 12/4, which is 3. Then 15/4, and I'm just continuing that pattern. So 18/4 would be 9 over 2, 21/4, 24/4, which is 6. And we would have the negative counterparts on the other side of the axis here. And because there's been no other change, this is actually going to look visually a lot like the parent function, but it's technically not because I've changed that x scale. So here's the points, and normally where it's undefined, and then here's the next points. So we see this part of the curve going up. And then I have to remind myself that I expect a third point to finish that period of the function. If I finish it in the other direction as well. Okay. And so for the domain of this function, let's look again about where the asymptotes are occurring to list what x cannot equal. I have asymptotes occurring at negative 3 over 2, 3 over 2, 9 over 2. They would continue. These are 1 period apart, so you could take the difference between the numbers or look back up at your period, which is 3. Right? Yeah. So I need to pick an asymptote to start with and add to that how far apart they are, which is 3 in this case, k, and make sure I just state that k is an integer value. And then the range is all real numbers. All right, now we're going to look at how to write equations, just like we did previously. So the hard part for some of the tangent graphs, we'll be looking at where the asymptotes are to understand the shifting. So the period, we should know that relates to the b value but doesn't immediately give us the b value. We want to work through the same work we would with sine and cosine, the only difference being that tangent normally started with a pi parent period. It was then compressed or stretched by the b value, and that produced the new period, which in this case is 2 pi over 3. And so this is what I want to solve. So this equation for me would say pi over b equals 2 pi over 3. That would say that 3 pi equals 2 pi b. And that b is equal to 3 over 2. So I have a b value of 3 over 2. There's a vertical compression by a half, so I'm going to have an a value of 1/2. And there's a vertical asymptote at pi over 6. This gets really tricky. Think about your original chart. The vertical asymptote happens where it's undefined, and in the parent function, that always happened at pi over 2. Now when we transform this, we expect the pi over 2 to be transformed into pi over 6 because that's where an asymptote is happening. How that transformation was happening is that x could be multiplied by something as well as added or subtracted with something. Okay. So far, we know that the b value was 3 over 2, which means x would have been multiplied by 2/3. So here's what we know. 2/3 was multiplied by the x value, which was originally pi over 2. And something, an h value, can be added or subtracted there, and that somehow turns that pi over 2 into pi over 6. So it starts as pi over 2, gets multiplied by the reciprocal of the b value, some mystery h value gets added, and we end up with pi over 6. That's what we know. And so this is the equation we're looking to solve. So this would say pi over 3 plus h equals pi over 6. If I subtract pi over 3 from both sides, I would get that h is negative pi over 6. And so my equation is going to say y is equal to an a value of 1/2. This is a tangent function. A b value of 3 over 2 times x plus, because this is x minus h, but h is negative, pi over 6. And it didn't say anything about a vertical shifting up or down, so I would leave my equation at that. We're going to look at the same thing for when we see the graph. So we're going to now visually see the graph, but we're going to try and collect this same information so that we can go through this same process to write the equation. So for the tangent graph here, okay, for tangent, I like to identify the period between asymptotes. So the period, notice, goes from negative pi over 4 to pi over 12. If you want to know how far apart those are, you take the larger and you subtract the smaller number. So that would say pi over 12 minus negative pi over 4. So that would turn into a plus. Pi over 4, if we make common denominators, is like 3 pi over 12. So this would give me 4 pi over 12, which is pi over 3. So the period here is pi over 3. Okay. If I know that the period is pi over 3, remember I have to think through this to get the b value. I know that it gives me the b value, but I have to do some work. Normally the tangent has a period of pi. It was stretched or compressed by a b value, and in this case produced a period of pi over 3. This means pi over b equals pi over 3, and b must be 3. Okay? So I know that the b value is 3. Okay? here are kind of the center of these tangent graphs. You can see the mark in between goes up to here, and on this side goes down to here. This mark is at 2, this one's at 3, this one's at 1. So they're only 1 apart. So that means there's no stretch or compression. So the A value is going to stay equal to 1. So I have my A and my B. I'm now looking for my H and my K. So my K is where the midline is. Notice this function, the middle points don't sit on the x-axis, they sit up at 2. So there's been a shift up 2. And then lastly, for the H value, it could vary. You could write a tangent equation. We could all write different H values, but if we chose them correctly, we could type them into Desmos and all get the same graphs that could look like this one here. So in order to find my H value, remember what gave that to me over here? What gave it to me over here was knowing where a vertical asymptote was. So I'm going to focus on one vertical asymptote here. In this case, I'm going to focus on pi over 12. And I'm going to think through the same things I did earlier. Normally, pi over 2 was the place where my parent function was undefined and gave me a vertical asymptote. I now know that whatever happened to that in the new chart, it's pi over 12 that's giving me that undefined. Okay. Well, what's happening is we're horizontally stretching or compressing, and then we're adding or subtracting some H value. So we already know that B is 3, which means we know that X is being compressed by 1/3. So here's what we know happened. We started with an X value of pi over 2. It's multiplied by 1/3. There is some mystery number added or subtracted, and we end up at pi over 12. I'm going to take what I just said and put that into equation. I started with pi over 2. It was compressed by 1/3. There was an H value added or subtracted, and then it ends up equaling pi over 12. So this would say pi over 6 plus H equals pi over 12. If I subtract pi over 6 from both sides, I will get that H is equal to negative pi over 12. So my H value is negative pi over 12. All of this information together tells me that if I write a tangent equation, it would say that y equals tan. Also look for your reflections. I'm sorry I didn't mention this before, but this tangent graph goes in the correct direction that we expect tangent graphs to go in, so it doesn't appear to have been reflected vertically or horizontally. So I'd have tangent of 3 times x minus negative pi over 12 plus 2. That would be the equation of my tangent graph.